Welcome to The Explainer. Today, we're going to skip the killer robots and all the sci-fi hype. Instead, we're going to look under the hood to see how data scientists actually build AI. You know, it's not magic. It's really more like a toolbox, and we're about to open it right up.
I mean, you see it everywhere, right? The term AI gets slapped onto our phones, our cars, maybe even our smart toasters. It's totally gone from being some obscure tech jargon to a household buzzword. But what does it actually mean when a data scientist sits down to build one of these systems from the ground up? Well, as you can see here, the reality is a little less dramatic. We are not dealing with conscious, all-knowing machines. What we actually have is something called narrow AI. These are specialist systems, and they're incredibly good at one specific thing, like recommending your next song on Spotify or understanding your voice commands. They're absolute masters of their one job, but they really can't do much else. So let's get started by separating the fact from the fiction. To really understand AI, we have to look at it through the eyes of the people who actually build it, the data scientists who are focused on solving real, practical problems every single day.
And that brings us to the core of this whole explainer. If AI isn't magic, then it has to be built with tools. It's kind of like a chef, right? They have a specific set of knives and pans. Well, a data scientist has a powerful digital toolbox for creating AI.
So this is the big question, isn't it? How do you go from just a big pile of data to a system that can actually make intelligent predictions? Well, the answer lies in something called a framework.
An AI framework is pretty much a developer's best friend. Think of it as a massive collection of pre-written code, building blocks, and libraries. You know, trying to build an AI from scratch would be like trying to build a skyscraper by forging your own steel. Frameworks, they give you the ready-made girders, the cranes, and the blueprints to actually get the job done.
And this is exactly what makes them a total game changer. Frameworks have really democratized AI, putting these incredible tools into the hands of way more people than just a few elite specialists. They offer pre-built components for complex models, they're already optimized for powerful hardware, and they let companies scale their AI systems affordably. So, in short, frameworks are what make AI practical for the real world. Okay, enough with the theory. Let's actually look inside one of these toolkits. We'll start with a really powerful and flexible framework called Apache MXNet.
So MXNet is really built on two key ideas. First, you've got the glue-on interface. You can think of that as a really user-friendly design studio for laying out the architecture of your AI. And then you have ND arrays, which are like these high-performance engines that hold and process all your data at absolutely incredible speeds. It's the combination of an easy design process with a really powerful engine underneath.
And this plot shows you exactly the kind of messy, real-world problem a framework can solve. See, we have three distinct groups of data, the green, the blue, and the red points. But the lines between them are super complex. The AI's job is to learn those boundaries so it can classify a new data point into the correct group. This is a fundamental task in AI called classification.
This all comes together in a really clear four-step workflow. First, you load your data into those super fast ND arrays. Then, you design your network using that easy glue-on interface. Third, you train the model by feeding it all that data. And finally, you use the trained system to make predictions on new information. Simple as that.
Now, let's switch gears and look at another one of the heavyweights, TensorFlow. This one was developed by Google, and while it solves a lot of the same problems, its underlying philosophy is actually quite different.
The core philosophy behind TensorFlow is this idea of a static graph. So what does that actually mean? It means that before you run a single piece of data through your model, you first have to define the entire computational blueprint. You literally build the whole factory assembly line before you even turn it on. So TensorFlow's whole static graph approach is built on three core concepts. And the first one is right there in the name, a tensor. Just think of a tensor as the raw material for our factory. It's the fundamental container for all the data, for all the numbers that your model is eventually going to crunch.
Okay, so next, that data, those tensors, needs a place to go. That's the graph. The graph is the full blueprint for our entire factory. Each node on the graph is a specific calculation, and the tensors are what flow along the assembly line, from one node to the next. The key thing here is that this entire map is defined up front before anything actually runs.
And finally, once you have your materials, the tensors, and your blueprint, the graph, you need to turn on the power. And that's the session. The session is the engine that takes that blueprint, feeds in the data, and executes all those calculations to produce a final result. It's what brings the whole static plan to life. And this architectural diagram really pulls it all together. See, up top, you have the high-level APIs like Keras, where a developer writes their code. That defines the blueprint, the graph. Then that gets sent to the TensorFlow distributed execution engine, which acts as the session, and it runs all the computations on all kinds of hardware, from powerful GPUs all the way down to the phone in your pocket.
So we've looked inside the toolkits of both MXNet and TensorFlow. Now let's zoom back out a bit and see what these tools actually allow us to create. Like, what problems can we really solve?
Ultimately, these frameworks help us answer some really critical questions. Tasks like classification answer, which category does this belong to? Just like we saw with that 3D plot earlier. Regression answers, what numerical value should this have? Like, say, predicting the price of a house. And optimization helps us find the single most efficient solution to a really complex problem.
So the main takeaway here is this. AI isn't magic, it's a craft. It's a discipline built on solid engineering principles, and these powerful frameworks are the toolkits that are making it accessible, practical, and revolutionary. They are what empower data scientists to take on these immense challenges and, piece by piece, build our future.
And the amazing thing is, these toolkits are getting more powerful and easier to use every single day. So that leaves us with a pretty big question. With these incredible tools now at our fingertips, what's the next big problem that we should try to solve?